Yes.
Can you all see the screen? Okay.
Phil,
Hey,
I don't think we can hear you.
oh, really?
I can hear you.
Tien, you need hearing aid? I don't know what happening.
Tim, did you hear me
Mọi người
when
trong
I talk?
xe. Yeah, I can hear you. And can somebody in the mọi người ở trong kia có ai nghe thì cho tôi biết được không ạ? Thiện không có nghe.
Yeah, I can see your microphone going up and down, but
you cannot hear.
Couldn't hear you, Phil.
But what about the whole team? I'm not sure what to do there. Is Dave there? Anybody else?
Yeah, I can hear you.
Yes, I can hear
Okay.
you.
Okay, all right. So Thiên, I think I'm going to go ahead. Okay. So xin lỗi mọi người tại vì tôi có một cái sự kiện mà tôi không nghĩ là tôi vào. Nhưng mà chắc là bị có lỗi về vấn đề mà communications. Okay, so we're going to go through the macro placement lecture 4. So we up until now we have done the import. We define the chip size. We define the placement areas for the I/O cells. Now we're gonna see how we're gonna place the macros, right? Oops. So the purpose of macro placement is to determine the positions of the macros, and you know what the macros is. So the purpose is to find out the locations so that you can have the best possible performance, power consumption, and area utilization. So you optimize the area utilization to minimize the wasted space and achieve a compact layout. You minimize the interconnect lengths. By doing so, you decrease the signal propagation delays, you reduce the power consumption. And then you will do it in such a way that the routing can be easy and provide a structured and well-organized layout. You will learn the concept of congestion, how to do the floor planning, such as the congestion will be minimized. And you can facilitate the efficient routing of the signals, the power grid, and the clock lines. You will be minimize the length of timing critical paths. We'll show you what that means for a faster circuitry and less area for timing closure. You will minimize the length of the frequently accessed signals so that when you switch less power, you use less power. So the first strategy is that when you have a lot of macros in your chips, you would need to find out what we call the data flow or the data flow diagram. From the high level chip definitions, right? For example, most of the processors have a von Neumann architecture in the old days, or the hybrid architecture in a few chips, and you're supposed to know all these. But in general, you have memories, that means data and program, and you have calculation unit to calculate the addresses or the data. And you have the data path that process signals and information and do things with it. You have I/O devices to communicate to the external world. This example is a DSP chip. And those who knows DSP, there's an inner loop called FFT. That involves the multiply and accumulation operations, meaning the data is read from two sources, multiply and add operations with a coefficient coming from a RAM with the instruction coming from a RAM. So when you do the floor planning with all these dual RAMs and coefficient RAMs and program RAMs, you want to group them such as the inner loop. This happened in a cellular phone, for example. You have a signal coming in, you sample it, you get a series of data that comes in and just keep on shifting and being operated upon. Just a process that clean up the signal, do some filtering, etc. So this happens, continuously when you turn on the phone and you're hearing, and communicating. So to do this right, and usually this is a speed path, meaning that because of the operations require computational unit, you want to be very fast, and you want low power. Cell phone, needs to save power. So if you do this one all the time, so you want to put all these guys together closer, and you look at the data path, where the data come from, where the coefficient come from, etc. So knowledge of this will help you reducing the wide lengths of timing critical paths, or the speed paths. You have wire length less. If you have less wire lengths, then you have less signal propagation delays. And so if you have less signal propagation delays, then you need less area for time enclosure. For example, if you have a long wire, you might need multiple buffers to make sure that the signal is fast enough. So if you have shorter wires, and you don't need that many buffers. And then all these frequently switching signals. In this case, the data being switched, read every cycle, and then store back to the result every cycle. You want to minimize that data bus, right? So all these knowledge about the data path, that structure, will help you have a better location for all these memories. And as a result, you have reducing leakage power because you have less areas of cells. You're decreasing the delays because everything is closer together. And you reduce the dynamic power because all your frequently accessed signals are shorter than thing. So this is the most important aspect of the micro placement. And then the next few things will involve a lot of various things. It's just by experience, you know that all these memories, when you place them, you tend to, is the best location is on the boundaries, on the periphery, leaving a very good continuous, what they call contiguous meaning that everything is connected together physically without interruption in between. So with a contiguous placement area, the efficiency of the router and everything else is maximized, meaning that it's the best kind of placement area versus fragmented, meaning you have a macros put in the middle, then now you have multiple areas that a standard cell can be placed versus a big and continuous one. Right. So that's one of the most important knowledge. And then you will place it in such a way you avoid notches. But notches is something like this, like a U shape, right? The reason for that is usually cells placed in here, and usually signals that's coming out in multiple places. You create a congestion area. It's not very, very good in terms of area utilization because you have high wire density. And high wire density tend to give you trouble in terms of routability and in terms of time enclosure. And so you'll learn congestion later when but present you with the placement step. And then another thing you need to avoid when you place all these macros is all these things. It's called chimney. Chimney means the area very long and narrow, right? And this also because of wire density. If you have pins where you have pins in between the memories, the pins have to be routed out, and you have tons of pins routing that have to go through this narrow channel. So usually you want to avoid these kind of area. And the next slide will show you how to avoid these. And then I'll pay attention to the wirings have to escape the stack of macros. So if you have a lot of wires here, you want to leave enough space for wire. If you cannot route over the macros, then you have enough space for the wire to escape. So and here are the different things related to pins. So you see if the pins facing each other, and if they connected each other, you try to have them face together so the wiring between them are minimized. And then you can see here, over here, if your pins, if you have a control, then you don't put IO pin, the micro pins in the corner here where the signal have to escape the narrow area to get out. So you want all these pins facing inward into the standard cell areas. And most of these micro pins interact with the standard cell area. So you don't want to put you don't want to orient this gram so that the pins are here, then since it have to talk to cells over here, it has to go a long distance versus you flip it and then you have shorter wiring. So those are the different things. And also in here, we talk about chimney. This is the one way to avoid chimney. You have two macros and you have pins on only one side, and you share and you abut them, meaning there's no empty area in the middle, so you don't have chimney. But if you cannot if you cannot avoid that, right, if you have these pins and they talk to each other, meaning you have to face them, then when you face them, you have to pay attention to this narrow area. You leave enough room for wiring to go out, because if you don't, then you waste area. But also, if you have this long and narrow areas, sometimes you have to have buffers in between if a signal coming here and go up there, the long wire, you might need to buffer them. So if you don't have a landing place for buffers, then you're in trouble. That means that the wiring have to be long and you cannot sharpen the signal. So if you have to have cells in the ear, then you can, to avoid having congestion, you can say only allow buffers, but you don't allow cells that with a lot of connectivities, and you add to the congestion. So you can play with different things in this area. And also, if you have cells that you have to feed them the signals, the power and ground, you need to make sure that they are receiving power and ground from the power grid. So you control all these placement by having what we call placement blockages. Placement blockage meaning that if you don't want cells to be placed here, then you block them. And there are different types, and we're going to go over different types. One is called if I don't. I think the later slide will cover those different type of blockages. But let's see what else. Yeah, or in here, you can either control by allowing buffers only, or you can say, you can give a low utilization. But we'll do that. One of the things that that you can do, I'll go about that later. But typically, areas around the corner of a macro or between some macros in narrow areas are subject to congestion. Congestion hotspot means that if you have to have wiring going through a certain area and you don't have enough areas for all the wires to go through, then you have a congestion. The congestion will create problems for you in routability, because if you don't have enough space to run many wires, then chances are you cannot have a DRC error-free layout. So you have to pay attention. The reason for this corner to be hotspot is that signals tend to come here, and since there are cells over here, it will turn the corner and go up here, and signal over here will need to turn over here. So by default, the tool will find the shortest distance between the two pins of a standard cell or a macro. But if they try to assign the wiring, near here, then you usually and you have cells over here, you usually have problems of areas in here, especially here also, right? Because we already know that. But so to avoid these things, two things you can do. One is you call placement halos, and I think we'll cover this halo, what it means. Halos means that if you move the macro, the placement blockage will move with them. But there's some other type of blockages that you only draw a shape, like in here, you draw a shape here. They say block the cell placement in this corner. So this can be potentially be a hotspot because of the reason we show here. And then you use something called Tien already show you a lot, right? Time flight line, so you know how it works. So so you if you use flight line, you see these two are connected to each other, you can pull them closer, like here, and if you see here, you place a macro here, but a lot of them are connected to the IO pins, and you pull this one closer to the IO pins. So another placement guideline will be here. Over here, you say avoid crisscross, meaning that you see this. If you turn them, then they will be aligned like this, versus go left, right, left. So you pay attention to these by showing the flat line, and pitch be right. So if you have narrow areas in between the macros, then you use some kind of formula to determine what is the optimum space between them. And after you're done with all these things, you do put a fixed attribute to all these macros. The reason why you need to do that is that if you don't do that, the placement step. Placement means the tool will determine the optimum location for all the cells, including macro cells. So if you don't put a fix, meaning don't move, then the tool will move this around and mess up your placement. So you do want to put a fixed attribute on these macros after you're done. Another note will be the some advanced, some smaller geometry like 22 and smaller, you need to have orientation, the same orientation probably due to process control. So if your design rule require poly to be in just one direction, then all your macros have to be placed just only one orientation, two orientation, but with one poly orientation. So you need to pay attention to that. So do find out what this means. What means is that if you look at a transistor, the poly is a gate, right? If you look at the gate, if a poly is vertical, then all the gates on the chip, including gates inside the memories, they have to be one single orientation, meaning vertical. If they are horizontal, then they are horizontal. You cannot mix them. So I think I cover all the macro placement, and then we mentioned about placement blockages. This is a little bit more details on placement blockages. So there are different types. We already talked about halo. Halo is say you pick a memory and you say put a halo. Halo means so halo So you put a blockage with certain micron away from the edge of the macros, and you just do a create place halo command. And then this is a soft blockage, meaning if you place a macro here and then you want to move them later in a different area, yeah, you don't have to redo the blockages. The blockages will follow relatively to the macros. But on the not halo ones, then you have to define really the box, bounding box that you want the blockages to be in, and that different ones, like a hard placement blockage, meaning nothing can go in that area. If you draw a box and say this is a hard placement blockage, nothing can go in there. But if you say it's partial means that you can have a smaller than any kind of utilization. It's called maximum utilization. It means if you say create a placement blockage type partial, and you say 50%, that means that only the maximum it can go is 50%. It's like that's a whole every more if you have 20, then if you less. So this is a way for you to control the placement of the cells to manage the congestion. If that you control the type only, but you don't control the utilization. You say any type can go in here in a normal placement area, but if you say soft and you say probably the default will be blocking everything except allowing buffers, inverters, clock gators, for example. That's some default of the tool. So basically say you don't want any logic in the area, but you have a need to buffer the signals, and you have a need to clock gating yes, but basically these are the cells that are needed on every signals, but you can block a certain like logic signals, logic cells, and only allow these important cells in the area. So you create a placement blockage called type soft. And then there's a placement blockage for macro only, and we don't use it because most of the things that we do, we just place a macro manually. But if you have a tool that can place the macros very well, then you what it means that you don't the create place blockage is the command that is used. And yeah, so it's a way for, this is an example. If you have a lot of pins on the left and then on the right, and you have signals
This meeting is being recorded.
and areas that you have you can route, because the cells you will have include the signals. That signals need to be routed. So be moving the cell out, then you have plenty of other routing resources, right? And this is an example that Tian already went through, and you guys already went through the lab, right? So you do relative placement, but you pick a point where you start everything from, and like a starter macro, and then you say build, if the same macros, and you say build an array of 5 by 5, and where each of them will be spaced from each other a certain distance away, and then all these things will be done automatically for you, so it's you use so you start with an anchor point and an anchor macro, and you define the array, right? Like I said, the in here 4 by 5, for example, and then you run this create relative command, a relative floor plan command,
This meeting is being recorded.
Changing sizes, or you have a new net list that you have different ways of doing things, and you don't have to redo all these things by hand, but you can just execute the commands. So and then remember, after you're done, you put a fixed attribute to block the to stop the tool from automatically place them. Move them later. So that's about it. And macro placement is very important, but the other is relatively simple compared to the real placement. But those are the things to watch out for, and you will find more things that that will be needed for your particular chip. But that is something that is always the case for any kind of design. So with that, you complete the next step. Oh, there's a check mark. So you complete this check mark, and you're ready to define the standard cell areas. And you learn that one that in very complex and performance-driven chip, sometimes you use machine learning, you use AI within the tool to help you with the macro placement. And something you need to be aware is not applicable for, it's not useful for simple design, but for complex design, a few high performance design houses been trying this machine learning tool, meaning that the tool will place it.
This meeting is being recorded.
The end, it will say, based on my analysis, based on my learning, based on the models you provide, this is the optimum result. So they spit out at the end your macro placement. And that's something to be aware. But for mixed signal IoT type of design, not microprocessor design, then we haven't found the justification to use that yet. Based on the simplicity of our design, and also based on what the tool can do for our design. So so I think that's it for our lecture today. You have any question? All right, it doesn't look like we have any question. How did it go the first hour? It looks like we finished early. Tian, anything else we need to cover?
Phil, there's a question for you
Oh, where's the question? Yeah.
in the chat.
Let's see. Can you talk about the poly orientation part? Okay. Yeah. I don't have a demonstration. Let me see if I can just draw. I need to share again. I don't have the. Can I use my finger? Let me see if I can use finger. Okay, I can use my finger. All right, so if you have a transistor, right? So you have polys and you have diffusion, right? So this is a poly gate. Sorry for has been tilted, but you have an inverter, right? So you have a P transistor and then you have an N transistor, right? So the orientation means this is the gate is in the poly gate here. It's you call this is vertical, right? Go up and down. So in your macros, you have you have transistors.
Are you sharing?
Huh?
Are you sharing on Phil?
Sorry, I didn't hit the word share. Right, sorry, I have to do it again. Okay. So let's try again. So as you know, a transistor is made of poly and diffusion, right? For example, it's an inverter. You have an P channel here, and you have an N channel, right? So you have the gate, you have a source and drain, right? So for example, this you have the source here connected to VDD. This is you have connected ground, and then you have the input coming in A, and you have the output. You have the output connected here, so you have a Y here. So this is an inverter, right? Y. So the gate of the inverter is really the poly, right? So these things are going up and down. So this poly orientation is vertical, right? So, but in your macro, you have transistors too. So your macros will have certain orientation, but for certain technologies, because of process control, all the poly have to be in one orientation because of the process control will be messed. When you build a circuit, it's important that your shape is built really correctly, and sometimes because of because of the photography, if you to control the uniformity of all these shapes, sometimes you have to have certain limitation in terms of how freely your layout can be. For example, if your poly is vertical and you have another poly that is horizontal here, the presence of this poly relatively to the other poly will affect how the shape is formed in real life, right? So in real life, it's not going to be like rectangular like this, but in real life, the shape can just have some very because you're etching, right? So the proximity effect, by having different shapes and different orientation might mess up what the final layout to look like. So in some process, it requires you that you don't have this kind of orientation mix, right? So you have to be either you have to be either just one direction or the poly and vertical or horizontal. So if you have a macro here, right, and all your poly is like that, and you have standard cell here that poly is vertical, then you're good. But if you have standard cells vertical, and then because of the floor plan, you have to rotate. Yeah, you have to rotate the macros, and now your macro orientation like this. The inner transistor are probably like this. Then you violate the design rule. That's what it means. I hope that answers your question. Can you explain why introducing clock skews is the reason the designer prefer to place high performance, high power consumption macros away from each other? That is not the correct answer. It's not introducing clock skew. I don't know what makes you think that is the right answer, but basically, no, the right answer for placing high performance, high power consumption macros away from each other is for the reason of the voltage group, right? So if you have a chip, right, and you have VDD, VSS, is for example in one corner only. So you have VDD and you have VSS. And then you have a macro. Your macro would draw certain power, right? Because you have transistor that draw power from the VDD. If it draws too much power, then the R and the C, right, going into it will create some kind of IR drop, right? So if you have a macro that draw a lot of current, right? Meaning I is big, right? Then if you put it away from the source, the VDD here, VDD path here, then your R will be big. So if you have big current and you have large R, then your IR drop will mean that if you look at the VDD here, so if you look at the transistor and you have look at the VDD at the macro, then because of the R and the C going away from the pad, VDD pad, then the IR drop here will become, so if you look at the signal here, instead of VDD, when this transistor turn on, it will be, because of the IR drop, it will droop down and go back up when you don't turn this transistor on. So by having this macro far away from VDD, then your droop is bigger, and in some cases it can exceed your goal. So what you want to do is put the macros closer to here, to your source. So that means that your R is, the current is always the same, but the R is reduced, so your droop is no longer big, right? So so that's the correct answer. High performance and high power consumption meant the same thing, meaning that if it draw more current, right? Okay, any other question? All right.
There's not a reason. There's no reason that sometimes you want to keep the high performance and high power consumption macro or block away from each other to dissipate the heat. The heat, because well, the high power, high performance, high power block will generate a lot of heat, and sometimes you want to spread it out. It is to keep them in one place. That may have the impact on reliability of the part for when the chip is aging, meaning when over the years, when the chip used in the end product, especially for the chip that used in automotive or in industry, when it run for a long time, it will the high heat, and you want the heat to be spread out evenly than to concentrate in one area.
Yeah. I'm glad you mentioned that because I think I misunderstood the question. So, yeah, I didn't answer the question. Yeah, that's correct because you're talking about, oops. So you're talking about two macros. I was talking about VDD, VSS. Yeah, correct. Yeah, so Boo had a good point because if you have high power here, so when you have a lot of current drawn to this, right? So locally you have heat spot here. Locally you have heat spot here. So by having them away farther away from each other, say if you have VDD here, if you have VDD path, man, no, it's so if you have VDD and then you have RNCs, right? IR drop. So if you put these two close together, then your IR drop will become more for this local spot, and also the the local heat. Yeah, the thermal management is another reason why you want to keep them away. Yeah, but you can only do that if they don't impact timing, right? So.
Yes, absolutely.
Yeah, I hope today we have more questions because we've been asking people to ask more questions, right? So, yeah. Anything else anyone can want to ask? The lab lead, you have any problem with the labs, or you have questions that you want to bring up here so that students can benefit from the answers? And you explain pre-assessment. Okay. So pre-assessment is a model of flip class, right? So the purpose of pre-assessment is that when so the process is, maybe I can draw, right? So flipped classroom, this is your class. Where is that? This is your class, right? And this is the class day. And this is before class day, right? So the traditional method is that when you teach, and then you practice and you do your homework. That's a traditional method. But the new method is that you want to make sure that in your class day you do mostly practice. So what you do is that you have a pre-class material that includes slides, like some videos and everything here. So you watch them beforehand, and at the end you do the pre-assessment. So it means that you learn most of the time by having this pre-class material. You read, you watch, and you do all your investigation, go back and forth, and you do this pre-assessment. So the outcome of this pre-assessment will determine what we need to teach before we practice. Okay. So the advantage of this is that we can spend a lot of class time for really teaching you how to do things with the practical results, versus spending a lot of time just teaching you the concept. We try to do that at the beginning, and we never have enough time. 2 hours go by very quickly. With this flipped classroom, you can spend and rewind, especially when you have limited English capabilities. So when we teach in class, it goes by real quickly and you don't understand that there's nothing available for you to review because you cannot just take fast enough notes. So having all these pre-class materials allows you to go back and forth and revisit and watch slowly or watch fast, or if you already know, you don't have to spend time. So we find even in USA, this flip classroom is really popular. But for the Vietnam case, with the English limitation, it's even more beautiful to use this thing. So at yeah.
I'm sorry, Charles, cut you off, but we are running out of time. I think that the student, maybe I also misunderstood the question too. The student actually want you to go over those questions that used in pre-assessment.
Okay.
Not to explain the concept,
Okay.
the need for the pre-assessment. The question today, all
okay.
the
Yeah. Okay.
Do you have that prepared for today?
I don't have it prepared for today, but we can do it next time. But it looks like there are some other questions. Let's see if we can answer those questions first. All right.
Okay. So we will
Maybe,
go over
yeah.
to resolve. I mean, to go over the question for this class in the next class. Okay. But let's spend the last like 5 minutes to address some of the related question here.
Yeah. So can we change positions of pins in macros? The answer is no. Macros are pre-designed IPs, right? So it comes in and you by law, by legal matters, you cannot do anything with the IPs you buy. But if you internally design the macro, then yes, you can. You can talk to whoever designed the macros and you say, hey, can you change this? Then yeah, they have to re-verify all these IPs. So I want you to solve the multiple choice question. Okay, that's what it clarified. Okay. All right. You say macros could not rotate due to fixed poly orientation. In slides, we have recommend that macros should have rotated to correct PNCI. So yeah, Ngô Quốc Thái, good points, but the message is in the methodology is that you can do all those rotation if you're allowed, right? If you're allowed, but if you're not allowed, you cannot do. But keep in mind, poly orientation doesn't mean that you cannot change the position, for example. So when you have a macro, you notice that there's some angle in between. That means this is 0, 0. Oh, and this is orientation 0. But poly direction mean that you cannot rotate 90 degrees or clockwise or counterclockwise, but you can flip, right? So it means that you can have the macro flip like this. So your corner is right here, your 0, 0 is right here, but versus 0, 0 right here. But you cannot rotate for sure because of the of the poly limitation, right? So okay. All right. Any other questions? I love the questions, so thank you so much for asking. Those who ask questions will be remember. Your names will be remembered. Okay. Thank you.
Bonus point.
What's that, Vũ?
You get a bonus point.
Yeah, bonus point. So Võ Tuấn Minh, Ngô Thị Khiêm, Ngô Quốc Thái, and maybe other people in the yeah, in the past. Okay. Yeah, Ngô Thái Anh Hào, Nguyễn Văn Duyên. Even you say, can you share the screen? It still have bonus. Okay, it looks like we have 3 minutes left. If there's no more questions, I assume everything goes well, right? Any
Yes.
last minute comments? You
Yeah,
can talk in Vietnamese, right?
Yeah, I just want to add another comment. That's just related to the question about the orientation of the macro block. When we architect the chip, sometimes for some of the special I/O segment, like the DDI interface or the MIPI display or MIPI camera interface, which basically the interface to the display panel or the interface to the camera sensor, though a very high speed I/O signaling, and sometimes we want to customize, or you want all the I/O come out in a certain pattern. So we had to order the design team right upfront that this is the order pin that we want to see it come out. And sometimes we even wanted to come out either one side of the chip or wrap around a corner of the chip. So though we can order upfront, and the design team will implement or design the circuit the way that we want it. Or if we license the IP, we can request IP vendor to custom design the block in the not only the size but orientation that we want it to come out, so it can fit into the pattern. So that's just a comment that whether we not we can dictate the orientation of my macro block.
Thank you, Vũ. There's some comment. Why don't we receive the IPs at the netlist level to do physical design by ourselves? Võ Tung Minh, yes, very good question. What we call soft IP, not the netlist, but you will receive the RTL. So as you recall, right, the process, you start with RTL, right? This RTL is a register level transfer, meaning that it contains information on the cycle basis only. But if and then the process is you go through synthesis, right? This is synthesis, and you have a gate level netlist. This gate level netlist is the one you fit in the place and route, right? And then you go to final layout before you tape out. So this gate level netlist is what you're talking about, but so IP comes in two form. One is the final layout. Two is from the RTL level. The reason for RTL is that RTL is technology independent, right? If you do synthesis here, when you do synthesis, you say you have to do like you have to do 22 nanometer here. It's a technology already attached to this netlist. So, but if you have a soft IP that have a RTL that doesn't tie to any technology, then you can go through this process yourself, right? So, so the whole thing is called soft IP. Very good question. Thank you, Minh. All right, looks like we run out of time. Thank you for all the questions again, and yeah, I guess
Thank you, everyone. And have a good day. Have a nice weekend.
Yeah. Bye-bye, everyone. See you next week.